Modern art as steel twists, flame bursts, and components vanish in a puff of smoke. For years, SpaceX was blowing up more rocket engines than most entire nations have ever built. And then, silence. Today, you're going to discover exactly why the Raptor engine used to explode every other week, and the 7 insane engineering leaps that transformed what many called the most failure-prone rocket engine in history into arguably the most reliable mass-produced rocket engine on Earth. Stick around to the end because the final fix is so elegant that it gave Elon Musk goosebumps on stage. To understand why Raptor kept failing, you have to first understand just how different it is. This isn't an F1. This isn't even an RS-25. Raptor is a full-flow, staged combustion methane-oxygen engine running massive chamber pressures, around 30 megapascals, roughly 300 bar. That's 50% higher than the Space Shuttle main engine, which itself was already pushing the limits of material science. Imagine stacking 3 Boeing 747s on your thumbnail. That's the pressure load the engine chamber walls are dealing with. The Raptor's thrust target started at 230 tons, later climbing past 280 and heading toward 300 tons in Raptor 3. Every ignition involves turbines spinning at over 30,000 revolutions per minute, pumping cryogenic methane and oxygen through fiery preburners. It's like starting a hurricane inside a metal box and expecting that box to survive it, cool itself, and then do it again 100 times. In the early days, it didn't survive. It blew up. A lot. SpaceX didn't just have a few explosions. They had hundreds. Turbopumps shattered, copper melted, shafts seized, gaskets failed, valves jammed. It was chaos. But that chaos produced data. Every single fireball became a lesson. Each destroyed engine made the next one better.
In 2017, the first Raptors were borderline experimental. Raptor 004 famously shredded itself when a turbopump spun up uncontrollably. In 2018, another engine's oxygen pump disintegrated mid-test. 2019 saw a unit literally launch off the stand in McGregor, Texas, turning the entire facility orange for a few terrifying seconds. By 2020, early Starship prototypes were exploding in South Texas. Header tank issues, feed line ruptures, sensor faults. If it could go wrong, it did. By late 2021, things looked bleak. Leaked emails painted a picture of crisis. Musk himself called the program a disaster and warned that if they didn't fix Raptor, SpaceX could face bankruptcy. The phrase Raptor meltdown wasn't a joke. Dozens of combustion chambers melted that year. Twitter nicknamed the engine rapidly appearing pieces all over Texas. Engineers joked that you could measure progress by the size of the craters at McGregor. Why was it happening? Because the Raptor was trying to do the impossible. Full-flow staged combustion is the holy grail of rocket engines. It burns both propellants in 2 preburners, sending one fuel-rich and one oxygen-rich stream into turbines before combining them in the main chamber. That means both pumps operate under extreme heat and pressure, with almost no tolerance for mistakes. The fuel-rich side runs hot. The oxygen-rich side runs hotter. One micro crack, one misaligned seal, and boom. Most countries avoid this design entirely. The Soviet Union tried in the 1960s. The US tried with the integrated powerhead demonstrator in the 2000s. It never flew. SpaceX not only built it, they built it to be reusable and mass-produced. That's like designing a Ferrari engine that can survive 100 drag races and cost less than a lawnmower motor. Methane adds another layer of difficulty. Unlike kerosene, methane doesn't leave residue. That's great for reusability, but it behaves differently thermally. It can freeze valves, cause vapor lock, and is harder to ignite cleanly. Combine that with 300 bar pressures and rapid restarts, and you've got a chemistry set that wants to kill itself.
And then there's clustering. The super heavy booster doesn't have 1 or 2 Raptors, it has 33. That means one bad startup can cascade across others, like firecrackers in a box. During early static fires, chain reactions were a real fear. But instead of retreating, SpaceX leaned in. They adopted the build fast, break fast philosophy. Every failure became a line of code in the next design. The test cadence ramped up until McGregor was roaring daily. The engineers treated the Raptor like software. Patch, relaunch, repeat. And over time, something miraculous happened. Failures started decreasing. Tests started running longer. The explosions got smaller, then rarer, then gone. By late 2023, they were testing dozens of engines with minimal downtime. And then came the breakthrough flights. October 13, 2024, Starship Flight 5. All 33 Raptors ignited within 0.3 seconds. 0 engine outs. The booster not only launched, but returned and was caught by the tower. That was the moment SpaceX crossed from chaos to control. A month later, Flight 6 achieved the first in-space relight of a Raptor vacuum engine. By 2025, multiple flights recorded 0 failures. How did they pull off this turnaround? 7 engineering fixes, each one a major leap forward. Fix number 1, integrated plumbing. Early Raptors looked like spaghetti factories, hundreds of external pipes, hoses, and welded joints. Each weld is a potential failure. SpaceX redesigned the system so the plumbing runs inside the engine walls. The channels are machined directly into the structure, cooling the walls and eliminating leak paths. This one change removed hundreds of potential weak points. In rocketry, simplicity equals survival. Fix number 2, deleting the heat shield. Early Raptors were wrapped in bulky sheet metal heat blankets to protect against radiant heat, but these shields added weight and complexity. With improved cooling flow and internal channels, the Raptor 3 design no longer needed them. The result? About 650 pounds saved per booster and fewer components to fail. Removing parts is the ultimate reliability upgrade.
Fix number 3, ignition redesign. Early Raptors used torch igniters, small pre-burners that sometimes failed to light or overfired. They were replaced with dual redundant spark igniters, solid state, no moving parts, simpler, faster, and nearly foolproof. Ignition reliability skyrocketed to near 100%, ending a major source of early engine losses. Fix number 4, 3D printed turbopumps. Turbopumps are the heart of a rocket engine. They take cryogenic fluids and slam them into the chamber at insane pressures. Machining these parts traditionally introduces micro defects that cause fatigue and cracks. By switching to 3D printing, SpaceX improved precision, reduced material waste, and increased durability. These new pumps can handle higher stress, run cooler, and last longer. Fix number 5, the nitrogen purge. During shutdown, trapped oxygen pockets were causing small fires around the engine bells. SpaceX added an automated nitrogen purge. It flushes oxygen after each burn, preventing post-shutdown ignition. Simple, effective, and cheap. It's one of those why didn't we be this sooner fixes. Fix number 6, live bolt monitoring. Vibrations during flight were loosening critical joints. Instead of overbuilding everything, SpaceX added strain gauges to monitor bolt tension in real time. If a joint starts to relax, sensors detect it instantly. That feedback lets them design lighter and safer. It's mechanical telemetry, small, smart, and elegant. Fix number 7, vertical integrated testing. For years, Raptor tests were done horizontally. That's fine for static data, but it doesn't replicate gravity, fuel slosh, or vibration. SpaceX shifted to vertical multi-engine testing, simulating real flight loads. Suddenly, new failure modes appeared, ones never seen before. And once seen, they were fixed. This one change uncovered the gremlins that only flight could reveal.
Put together, these 7 fixes transformed Raptor from fragile prototype to workhorse. Integrated plumbing cut leaks. Deleted shields reduced weight. New ignition ended startup failures. 3D printing boosted reliability. Nitrogen purge stopped fires. Bolt telemetry prevented structural loosening. Vertical tests caught hidden issues. Each step chipped away at the chaos until all that remained was confidence. By mid-2025, the data was clear. Raptor 3 engines were averaging multiple full-duration burns with 0 incidents. Production lines were spitting out as many as 9 engines per day. The boosters that once exploded were now catching themselves in midair and flying again. That's not evolution, that's revolution. The significance goes far beyond SpaceX. No company in history has ever taken a full-flow, staged combustion engine from explosive infancy to industrial maturity this fast. The Soviet NK-33 took decades. NASA's SSME cost billions per engine. Raptor hit mass production while improving reliability. It's not just a technological leap, it's a manufacturing philosophy. Why does this matter? Because reusability doesn't work without reliability. Every failed engine costs time and money. Every successful engine lowers cost per flight. When you can reuse 33 engines dozens of times, your cost per launch plummets. That's how Starship will move cargo to orbit for a fraction of today's prices. And with that reliability comes cadence. You can't launch weekly if you're rebuilding engines monthly. Now with robust Raptors, SpaceX can turn around boosters like airplanes. Service, refuel, relaunch. It's the path to true space logistics where rockets are tools, not miracles.
The Raptor engine also sets the stage for Mars. Methane isn't just a choice, it's a strategy. You can make methane on Mars using the Sabatier process, combining carbon dioxide from the Martian atmosphere with hydrogen from ice. That means Raptor can literally refuel itself on another planet. No other rocket engine in history has been built with that goal in mind. So when people call Raptor the engine that changed everything, they're not exaggerating. It represents a fundamental shift from custom-built to mass-built, from fragile to industrial, from experimental to operational. The same engine that once melted itself into puddles is now powering the world's most powerful rocket, reliably, repeatedly, and beautifully. SpaceX didn't get here by luck. They earned it through explosions, sleepless nights, melted hardware, and relentless iteration. Every time a Raptor blew up, it whispered a secret. The engineers listened, they learned, and they built the next one better. That's how innovation actually happens, through fire, failure, and persistence. When Elon Musk stood on stage during a Starship update and said the Raptor 3 gave him goosebumps, he wasn't exaggerating. He was looking at a piece of hardware that embodies every principle SpaceX stands for: bold design, rapid iteration, and the belief that nothing is impossible if you just test enough. So next time you watch a Starship roar off the pad and see those 33 engines ignite in perfect unison, remember the years when they didn't. Remember the test stands that blew apart, the melted chambers, the sleepless engineers in Texas. Because that's how progress looks. Messy at first, perfect later. The Raptor is no longer the engine that explodes. It's the engine that endures. It's the engine that will take us back to the moon, to Mars, and maybe one day across the world in under an hour. So drop a comment right now. Which fix impressed you the most? The internal plumbing, the 3D printed turbopumps, or that genius nitrogen purge? Smash that like button if you love engineering that doesn't give up, and subscribe for the next deep dive, where we'll break down the full 22-minute booster catch sequence and reveal the hidden tech inside the chopsticks. Until then, keep looking up. 3, 2, 1, ignition.
Photoshop just